Okay, so without further ado, we're pleased to have Dozier, who's going to talk about translation surfaces with independent short cells.
Yeah, actually that was the old title. But, so, this is that. New title is Convergence. Siegel Veech constants. So this is going to be a talk about counting problems on translation surfaces. So X is going to be a translation surface. And so n of xr is going to be the number of cylinders on X of circumference at most r. So then a Siegel Veech constant is supposed to measure the average behavior of this function. And so to define it precisely, we need a theorem of Veech. But first, so we're going to be doing averages, so we need to have some measures to average. So we're going to let mu be a ergodic, SL2R invariant probability measure on a stratum H. Okay, so then, so to define the Siegel Veech constant, we have this theorem of Veech, which says that, so for any such measure, there exists this constant, the Siegel Veech constant, depending on the measure, such that, so if you look at the average of this function n of xr with respect to this measure mu over the whole stratum, that this equals this constant, so mu times r squared. And so the point of the theorem is that this is true for all r greater than 0. So this allows it, so this constant doesn't depend on the r that you choose. So then, so there's this theorem. So right now it's just kind of this average, but it turns out that somehow the average behavior tells you what happens for almost every point with respect to the measure. So Eskin and Dozier proved that for mu almost every x in H, that so the asymptotics of this function n of xr, and so it grows asymptotically like c of mu times r squared as r goes to infinity. Okay, so what I'm going to, the main theorem I'm going to talk about is has to do with the kind of continuity property of these constants. So okay, so if you have a sequence of measures, so un convergent to mu, and the natural kind of notion of convergence is weak star convergence. then the Siegel Veech constants of the measures converge to the Siegel Veech constant of the limit measure. So if you think of the Siegel Veech constant as kind of a function on measures, it's a continuous function. So this was known for the, so I'm studying like more, the thing that I've defined here is the cylinder Siegel Veech constant. So you're counting cylinders, but you can count saddle connections, or you could count cylinders weighted by area, or there's a number of different variations, this kind of thing. And so this was known for the area Siegel Veech constant, where you're counting cylinders weighted by area, by Mateus, Muller, and Yakos. And so, but the area Siegel Veech constant has this very kind of special connection to Lelievre of exponents and the curvature of the determinant of the Hodge bundle. And so there you use, so you know, they study all those things, and it kind of comes from that you can get this convergence. But in general, you don't have, if you're just studying the cylinder Siegel Veech constant, say, or a lot of the other ones, you don't have those connections. So, so the proof that I have is more, it's much more sort of general. It doesn't use any of the kind of special properties of the area Siegel Veech constant. So I'm going to talk about the corollary now of the theorem. So you can basically, you can apply this theorem to Teichmuller curves in GS2. So specifically in H2. So we're going to let, so these eta k's be the measures associated to all the Teichmuller curves in GS2, in H1, in H2. So I mean, you just say order them all somehow, and then, so for each one there's kind of a canonical ergodic SL2R invariant probability measure, and so just take that. So then these converge to, the Siegel Veech constants associated with these measures converge to the Siegel Veech constant of the Maser-Veech measure, which is the canonical kind of invariant measure on the whole stratum. And it's kind of this stuff. So this you can compute, and it's equal to n over pi with the normalization that I showed us here. So let me tell you a little bit of the history of this corollary. So this people have studied these Teichmuller curves a lot, and so Lelievre studied the arithmetic Teichmuller curves, the ones that come from square-tiled surfaces, and he has figured out a way of computing the Siegel Veech constants, and he proved this convergence, but for sort of limited, just a subsequence of all the Teichmuller curves. So he proved it's kind of a special case, and he conjectured this general statement to prove a special case for arithmetic Teichmuller curves. And then, so there are two types of Teichmuller curves. There's the arithmetic ones, and then there's the non-arithmetic ones, which are just the eigenform loci in H2. And Bainbridge studied those, and he similarly compute the Siegel Veech constant, and he kind of observed numerically that this convergence is probably happening, but he didn't prove that. So he kind of evidence for non-arithmetic. Okay, so this corollary, I'm going to start by just proving the corollary. So it's a straightforward kind of deduction from the the theorem, sort of given all the fancy tools that have been developed in the last 10 or 15 years. So the first step is, so we need to, to apply this theorem, we need to get the measures converge. So we want to show that the eta k, so step one is to show that the eta k is converged to the Dozier Veech measure. Okay, so for this we have to use the equidistribution theorem of Eskin-Mirzakhani-Mohammadi. Which says, so basically it says that if you have, so some affine invariant manifold M, and you have some collection of submanifolds, NK, affine invariant submanifolds, then if there's sort of a reason to hope that the measures associated with these might converge to the measure associated to M, then you're kind of always lucky and it always happens. So the statement is, so M affine invariant manifold, and you have some infinite sequence of submanifolds, affine invariant submanifolds, then the measures associated to the NK equidistribute, meaning they converge to the measure associated to M, provided that sort of M is kind of the minimal thing that you could have chosen. So provided no infinite subsequence of the NKs lies in some smaller affine invariant manifold. So, I mean, maybe you chose M to be way too big, and so maybe this was M prime, and you chose M initially to be this thing, then they would equidistribute in this M prime and on the bigger thing, but there's nothing else that they could have equidistributed in, and they have to equidistribute in the thing that you want. So this is a very powerful tool, and difficult to prove. And so we want to apply this to get this convergence, but we need to know that we need to sort of satisfy this condition. So, but fortunately in H2 we know exactly what all the affine invariant manifolds are. So by McMullen's classification, basically the only affine invariant manifolds are Teichmuller curves for the whole strata. And there's not a Teichmuller curve that's going to contain infinitely many other Teichmuller curves. So the only thing that we could hope for is to use, so basically H equals, M equals H, and the above works. So EMM implies, Eskin-Mirzakhani-Mohammadi implies that the Siegel Veech the measures eta k converge to the Dozier Veech measure, which is the canonical measure associated to H. So okay, so we've got the convergence of the measures, and then we just apply the convergence theorem. So then the convergence theorem there. Since the measures converge, the Siegel Veech constants have to converge. Okay, so that completes the group of the world. So, and you can do similar things in other strata. Some of them are kind of already known, and some of them probably aren't. But so this is kind of an example of how you can use this. So now I'm going to give at least a sketch of the proof of this convergence theorem.
So the sequence NK in the theorem, does it need to be order closures?
Yeah, these are affine invariants. So sorry, everything is an affine invariant submanifold. In other words, an order closure. Okay, so we have this. So what do we know? So we have this sequence mu n that's converging to mu, and so what does the convergence mean? So I said it's Veech star convergence, so which is kind of the natural thing. So it means that if you take a function and you integrate it against mu n, that should converge to the integral of f against d mu. And then so this should be true for all f continuous and compactly supported. So it seems like what we want to do is we want to just apply this definition with the n of x r function. So we want to apply f equals n of x r. And so the Siegel Veech constant is just a ratio of, so if you divide both sides of that by r squared, it's just a ratio of an integral of n of x r to r squared. And so if you could do this, you'd be immediately done. But the problem is that n of x r is not compactly supported. I mean, it's not continuous either, but that's a sort of minor problem you could fix. But so the not compactly supported part is a bigger issue. So in Teichmuller Dynamics, a lot of the kind of subtleties and interesting things come from the non-compactness of the moduli space, or the stratum, and this is kind of an example of that. So what you have to, so in other words, we need to prove this, we need to control what's happening to this function and the measures in the thin part of the stratum. So the thin part is the part where the thin part epsilon defined as the part, so all surfaces in the stratum, such that the length of the shortest saddle connection on x has length at most epsilon.
So the function nxl is even proper, right? If when x diverges, the function is porous.
I don't. No. I mean, yeah.
What was the question?
Yeah. It's not so clear actually, but I mean, sort of the only problem that could occur is if it diverges. But it's not. I don't know if it always. I don't know if it's proper.
The question was whether NXR is proper.
Yeah.
Just to put it on.
Right.
Yeah.
That's certainly kind of the only place where the bad stuff could happen. Okay, so that's the thin part, and so the complement of the thin part is compact. So sort of on the compact part, we kind of use kind of this, and then we need to control what's happening on the thin part. So in particular, what we want to show is, what time did I start? So we want to control the integral, or the thin part of epsilon, of n of xr, p mu n. And in particular, we want to show that this goes to 0 as epsilon goes to 0. But then the point is that we need this to be, turns out we need it to be sort of uniformly, meaning kind of independent of the ring independent of UN. So the thing we want to avoid somehow is like having some contribution to this whole average coming from surfaces that are kind of deeper and deeper into the thin part for later and later kind of measures in this subsequence. Because somehow that's not seen by this sort of thing for compactly supported functions. Yeah, so I'm, let's see. Yeah, so I won't, I'll just kind of tell you the technical tool that you need to prove something like this, and the technical tool will actually be used for something else as well, so kind of independently interesting. So, so basically, what you want to do is you want to look at, you replace kind of averages over the whole moduli space with averages over these GTR theta circles. So you integrate from 0 to 2 pi, and then you look at whatever L of GTR theta x. Actually, so yeah, there's some little exponent here. I think not very much like that. So we integrate this with respect to theta. So this is just, so GT is the Teichmuller G. It doesn't float, R theta is just rotating theta. So this is just integrating over a circle. And so we want to show that this goes to, so basically we kind of want to show that this sort of thing goes to 0 as t goes to infinity. And so the bound that we get is that there's some sort of somewhat complicated but sort of decaying term here. So there's a function that depends on the surface, and there's some constant here. And then this thing is, there's a negative thing here, so this thing goes to 0 as t goes to infinity. So this thing goes to 0 as t goes to infinity. And then there's this additive constant term, plus b. And the point of this is that this doesn't depend on the measure, so it's independent. Sorry, so it's independent of x. Which will sort of mean that you'll get independence of the measure. So if you take the limit as t goes to infinity of this quantity, it is bounded above by this. So let me just kind of draw a picture of what this is kind of saying. So, so here's a picture of stratum, say, and so kind of this is going to be sort of the thin part off to the right. So the 1 over L function is kind of going increasing in this direction. So one sort of consequence of this, but sort of similar meaning, is that if there's some sort of compact set in the thick part, such that like there's just a fixed compact set, such that even if you start with a surface that has a really, really short saddle connection here, if you look at a circle centered there, so it's going to kind of wrap around a lot. But the point is, the big circle is going to lie sort of 99% of the time in this thick part, and there'll be very there'll be some, but sort of small amount of time where it's in the thin part, but it's not going to be way too far down the thin part. But really, most of the time, it's going to be compact part. So somehow, this is sort of the recurrence result in some sense that you look at these circles, you don't get pushed farther and farther out most of the time. But there's a small kind of interval direction where you can kind of get pushed out. Yeah.
When you say the thing, the first time goes to 0 as t goes to infinity, what about x? Or independent of x?
Well, no, so it's dependent on x, yeah. But I mean,
so for any fixed x, it goes to it?
Yeah, right. Yeah. But the rate will be dependent on x. But somehow you replace, you relate this integral, so the integral over h of this, the limit of this t goes to infinity of this. So it doesn't, that depends.
Alpha is alpha.
Yeah. I mean, you should think of it as something like 1 over the 1. Yeah. So, So now let me tell you, so that's kind of the end of the sketch. And I mean, to get between here and here, you have to use Nemo's theorem and some other little tricks. But it's fairly straightforward. So this technical tool so it comes from, it's proven with the Eskin-Mirzakhani techniques. It's similar to what they do to prove, I mean, it's actually related to one of the ingredients that goes into that theorem. And it involves like looking at complexes of saddle connections and combining them. And so another, actually sort of one of the reasons that I first was interested in this whole kind of circle of ideas is for the following kind of thing, which is it's a strengthening of Mazur's original quadratic up or down on the number of saddle connections, or a number of cylinders on a surface. So suppose we're given this fixed stratum, and so then there exists some constant, just depending on the stratum, such that for all surfaces in H, n of xr is less than that constant times r squared. So for all big enough r, but the big enough depends on the surface x. So it's sort of so Mazur originally gave a quadratic upper bound where the constant depended on the surface. So here the constant doesn't depend on the surface, it's completely uniform. But then you have to, you have to make r really big depending on the surface. So the constant here doesn't depend on x.
Oh.
So it's saying somehow there's not like surfaces with asymptotically kind of arbitrarily many saddle connections.
The threshold depends on x.
Yeah, right, exactly. Yeah, the constant's independent. So, okay, so I'll just give you just a little example to see why you need the constant to depend. Oh, sorry, why you need the threshold to depend on x. So say you start with some torus, and then you glue in. And then you're going to glue in another kind of very small torus along a slit. So then you can find like 1 million cylinders on this torus, and then you can make them, choose the slit to be tiny and avoid those cylinders, and then glue this whole thing into here. And then you'll get like 1 million short cylinders on here. So you can get like 1 million cylinders of length less than or equal to 1 on a given surface in a fixed stratum. So certainly, you could make n of x1 be 1 million. So you're not going to be able to get this to be independent of x. But somehow as you make the r bigger and bigger, the effect, if you started with this thing, somehow for really big r, you wouldn't even sort of really notice that you had this really short subsurface that had millions of saddle cylinders on it. So I just want to end now with a couple of, so I'll just say, so the proof of this is sort of fairly standard techniques, kind of using this as the kind of key technical. So you use kind of the Eskin-Mirzakhani strategy with this kind of using this. So there's a couple of open questions. So the first is that, so what is the best C in this statement? So maybe I'll just highlight C just depends on the H. So I'm thinking about how does it grow with the genus or the complexity of the stratum. And a similar question is, so the convergence theorem that I talked about, the main theorem, is kind of implies that there's a largest and so the Siegel Veech constants associated to all the measures in a particular stratum kind of are bounded below or bounded above and below. So there's a largest and smallest, and it's also a closed set. So there's the largest and smallest Siegel Veech constant in each stratum. And so you can ask kind of what are the largest and smallest ones, and how, and also like how do they grow with the complexity. Okay, I think I'll finish there. Thanks.
Do you have an answer for the questions in H2? How is the convergence? Everything is more or less explicit.
Well, so for this last one?
For
the
all
first
them.
Oh, yeah, so let's see. So in H2, actually, no, I don't really. I mean, I think you could just look at the, I mean, in H2, it's like, I mean, you could look at the list, and I think they're kind of converging fairly quickly, so I think you can kind of see probably what it was. But to prove it might be a little bit hard. But it does, I mean, you know, it wasn't like they had to compute millions of the consistencies that converge it, so.
Should be at the very beginning.
Yeah, probably, yeah.
So you know that it's isolated points.
Yeah, I mean, well, in H2 there are. I mean, H2, so it's just one sequence converging to something else. So I mean, there's only one limit point. Like in H2, it's just going to be, there's going to be the measure for the C mu MV, and there's going to be some sequence converging to it. But that's the only thing that can be a limit point.
Can you explain exactly in this key technical tool how the statement is better than the original statement that was in Eskin-Mirzakhani-Mohammadi?
So they don't really identify, so this independence of x. So they show that this integral goes to 0. That this integral is bounded, but not, it's like for a fixed x, that like the supremum of this over all t is bounded, but not that it is independent of the surface x.
You're not saying it's independent.
Well, but there's the bound, so I'm saying, so they proved that the supremum for 1x over all t is bounded, but actually the supremum, the lim sup for over all x and t, we're taking the t kind of, the lim sup with respect to t, that's bounded. So our priority might have thought that maybe if you make x have really short saddle connections, it's still, for a fixed x, that this is kind of bounded, but this t goes to infinity, but the b would go to infinity.
So if vortexes work and you're more recent field on the side board, do you think you can find some C of H which is probably almost clearly not the best?
Well, I mean, yeah, I mean, you could, like, it's not like there's some inherent, like, unexplicitness or something about it. I mean, you could find some explicit thing, I think, from using, I mean, kind of going through the argument for this and seeing exactly what everything depends on. But it's, so the natural thing is some exponential big growing thing. And it probably, I don't know what the answer is. It's at least like, it's going to be at least something like g squared, g is the genus. There's some examples that kind of show that, but it's between g squared and exponential, I don't really know what the answer should be.
Okay, so I think we should